What's going on, Algebros? In this video, we're going to discuss some of the lingo associated with transformations. Let's get started. All right, so we talked about the inputs of a transformation and how they're going to be vectors. There's another name that we could call these inputs, and that name would be preimages, or preimage for singular. So inputs and preimages are terms that are synonymous with each other. Likewise, the output vectors can be called something else other than an output, and that would be an image. And these are terms that you typically see in those higher level math courses. So just more to add to the plate in terms of terminology there. Now, we're going to take a look at two terms that are probably very familiar to you. And those would consist of sets of the inputs and the output vectors. The set of all input vectors is called the domain of the transformation. So we talked about how transformations are kind of like the linear algebra version of functions, and regular functions have a domain, and likewise transformations have a domain. The set of all output vectors that a transformation assigns inputs to, or the set of all images, is called the range. So transformation has a range as well. Now there's another term associated with domain and range, and this one's not as familiar in a standard algebra course, but it is worth mentioning here. So sometimes the vectors that are output vectors consist of a certain subset of the space that they live in. So for example, we might get a handful of vectors from R2 as output vectors, but there might be some vectors in that space that are not outputs of the transformation. So we have something that's called a codomain, which is the set that consists of all potential outputs that a transformation could be assigning inputs to. So the range of a function is sometimes housed in a set consisting of more numbers or vectors. Numbers would be the case for regular functions, and vectors would be the case for transformations. And the larger of the two sets is called the codomain. So to connect this with some prior knowledge here, I'm going to sketch the graph of f of x equals the square root of x. So notice I'm using a regular function versus a transformation. And I'd like to show you the relationship between the domain, range, and codomain. So usually in a standard algebra course, we just worry about the domain and range. But lurking behind the scenes is also a codomain, which we typically skip, but not in this course. So we're going to sketch the graph of the square root function. And I'll sketch a little coordinate plane to get us going with that. And you may recall that the square root function starts at 0, 0 and kind of curves off to the right while slowly increasing to positive infinity. Let's talk about the domain, which I'll call capital D, and we'll write the domain using interval notation. The domain consists of all the x values being used to produce this graph, and the smallest of those x values is 0. And then the x values continue on to positive infinity. Otherwise, this graph wouldn't continue to the right. So this part of the x-axis is a visual of this function's domain. And in interval notation, it would be bracket 0, comma, infinity. Now, keep in mind, the range consists of y values. And the smaller of those y values is 0. And because this graph is increasing as we go to the right on the x-axis, all the positive y values would necessarily have to be y coordinates. So here's a picture of the range, which would be the positive part of the y-axis as well as the y value of 0. And so we actually have a matching domain and range here. But let's talk about codomain, which I'll call CD. The largest set of numbers that can contain the range, or the set of all possible y values we could get from this function, would be all real numbers. Now, we don't necessarily get every single real number as an element of the range. Okay, so that's why I'm saying all possible y values that we could get. But the largest number set that would contain the range that we're seeing there would be the entire y-axis. And for that reason, the entire y-axis would serve as the function's codomain. So you can think of it as like the largest set that would contain the range of a function. And in interval notation, that would be negative infinity to positive infinity. So when we are transforming vectors, input vectors into output vectors, or pre-images to images, we tend to say that the transformation is mapping. Okay, so a transformation will tell us, okay, take this input vector, send it to that output vector, and so on and so forth. And it's customary to indicate what spaces we're going between. So when working with transformations, we usually indicate what space we send all of the input vectors to. And this idea of sending is also known as mapping. Okay, so when we send a vector to an output vector, we are mapping it. So for example, let's suppose that we have a transformation T that maps vectors from R2 to R3. One way that we could write this out is by writing capital T colon, and since we're starting in R2, I'm going to write R2, and then we draw an arrow to the space that we're sending vectors from R2 to, and that would be R3. Now what this doesn't tell us is whether or not all of the vectors in R3 are going to be output vectors. So with that said, here's what we should always assume about this notation. The very first space that we write out, which in this case is R2, that's going to be the domain. Okay, this is where we're getting our input vectors from. And then R3 is the largest set of vectors for that dimension that could possibly contain the range. And so R3, in this case, will be the codomain. So let me give you a visual using what I like to call blobs. Here's a little blob that's going to represent the domain. And based on the notation written above, this is R2. Okay, just a little schematic for it, a little representation of R2. I'm going to put a couple vectors in there, or I'll do a few. Let this point represent a vector x, this point represent a vector y, and this point represent a vector z. These vectors will be mapped to a vector in R3. So I'm going to draw a little arced arrow representing the transformation T, transforming the vector x into the vector T of x. Now this is a vector living in R3. Likewise, when we transform the other vectors, they will be vectors living in R3 as well. Now let's say that all of the output vectors, or the transform vectors, are represented by this red blob. This would represent the range of the transformation. But in some cases, we are missing vectors from the space we're going to within the range. So there might be times where there are vectors that are not being used as the range, in which case those would be vectors that are part of the codomain. Right? And it also follows that these are part of the codomain as well. So what I'm trying to get at is that this range might be only a certain subset of the codomain. So if that's the case, then there are going to be some vectors in the codomain that are not images of vectors in the domain. Okay. Now the codomain is indicated by R3. So every vector in here is going to have 3 coordinates to it. And if there are some vectors that aren't images of these input vectors or pre-images, that's fine. They would be still part of the codomain but not part of the range. All right. Now when the dimensions of the domain and codomain match, so we don't have matching dimensions, but in the event that they do, we would call the transformation an operator. Okay, so as an example, if a transformation took vectors from R2 and mapped them to vectors in R2, because the dimensions of the spaces match each other, this would imply that T is an operator. And we'll discuss more on operators when we meet for part 2 of this section of notes. All right, in the meantime, let me know if you have any questions about this video lesson. Otherwise, thanks for watching it, and I'll see you next time.